Buenos días a todos, a todas. Hablo en nombre del señor decano, Antonio Bru, que no puede estar ahora mismo con nosotros porque está en una reunión de Consejo de Gobierno con el equipo rectoral y tampoco ha podido estar con nosotros la vicedecana de investigación, Eva Gallardo, que está ahora mismo en Lumini, en Francia. Entonces me pidieron a mí personalmente que diera la bienvenida y en eso me voy a limitar. Simplemente daros la bienvenida a la gente que está conectada online también, bienvenida a Telemática, y a todas las personas que lo vayan a ver luego de manera diferida, pues lo mismo. Bienvenidos a esta facultad de Ciencias Matemáticas de la Universidad Complutense de Madrid y en particular a este evento que yo me callo. Tengo que decir que me callo porque ya los organizadores darán cumplida cuenta de lo que vamos a disfrutar hoy. El decano y la vicedecana personalmente me pidieron que estuviera en su nombre, pues por varias razones. Y una de ellas es que, en particular, yo estuve de coorganizador con Pier Giulio Tempesta de esta serie de eventos antes, entonces pues no deja de ser una criatura a la que le tengo especial cariño, pero doble cariño además es pues la amistad que me une con la ponente, con Eva Miranda, de años, muchos años.
Demasiados años.
Demasiados, nunca es demasiado. Y para lo cual pues me da especial alegría el poder pues dar la bienvenida y agradecer a Eva el que haya venido a Madrid y a este coloquio y que comparta con nosotros un tema tan interesante. Pero como digo, bueno, pues las palabras voy a pasarlas a quien tiene que dirigírnosla, que es el organizador o la voz del grupo organizador de este evento. Muchas gracias, Pier Giulio.
Muchas gracias, Marco, muy amable como siempre. Bienvenidos a todos a este nuevo coloquio que se enmarca efectivamente en el cuadro de los Joint Mathematics Colloquios organizados y patrocinados conjuntamente por el Instituto de Ciencias Matemáticas, la Universidad Autónoma de Madrid, la Carlos III de Madrid y obviamente la Universidad Complutense de Madrid. Tenemos también los demás coorganizadores, el profesor Ignacio Burgos Gil, el profesor José Conde y el profesor Fernando Lledó, de las tres instituciones que coorganizan el evento junto a mí. Quería decir que efectivamente estamos agradecidos también especialmente al ICEMAT y a la facultad por la ayuda concreta en la realización de este evento. Tanto el decano como la vicedecana de investigación se han involucrado personalmente mucho y también, la verdad, Marco ha sido estupendo en esto, en ayudar. Y muy bien, y además, ya que estamos, quería también agradecer a Miguel Ángel Pradera, que en la sala de controles nos permite la retransmisión en directo en el canal de YouTube de la facultad. Hoy es un gran placer tener como conferenciante invitada a este coloquio a la profesora Eva Miranda Galcerán, que es catedrática de Geometría y Topología en la Universidad Politècnica de Cataluña. La profesora Miranda es una de las matemáticas españolas más reconocidas a nivel internacional y, por ejemplo, entre sus muchos galardones quisiera por lo menos recordar la cátedra CREA de 2016 y de la Comunidad de Cataluña y también en 2017 la Chaire d'Excellence ofrecida por la Fundación de Sciences Mathématiques de París. El ámbito de investigación de Eva es muy amplio y incluye geometría diferencial, física matemática, teoría de los sistemas dinámicos y obviamente también más recientemente hidrodinámica y informática teórica. Entre sus muchos logros también quisiera recordar la teoría de los B-manifolds, elaborada en colaboración con el profesor Víctor Guillemén del MIT de Boston, y efectivamente estas novedosas relaciones entre topología simplética e hidrodinámica, de las que va a hablar hoy, también en colaboración con Daniel Peralta, Francisco Presas y Robert Cardona. Y por último, también me gustaría subrayar el compromiso de Eva con la formación de jóvenes investigadores, porque ha dirigido 6 tesis doctorales y otras 3, creo, ¿no?, están actualmente en marcha. Muy bien, el tema de hoy es particularmente fascinante porque se trata de una conexión novedosa entre temas aparentemente muy distintos como la geometría de contacto, los flujos de Beltrami y por un lado, y por otro lado la informática teórica, las máquinas de Turing universales y en particular obviamente la dinámica de fluidos. Entonces, muchísimas gracias por participar y por obviamente aceptar nuestra invitación. El seminario creo entonces va a ser en inglés, ¿no? Salvo cambio de última hora, y entonces, let's switch to English. Thank you very much, Eva. And so I leave you the floor, and please, you can start at any time you wish. Thank you.
Thank you very much, Marco and Pier Giulio, for this invitation. Gracias a todos por asistir. Pier Giulio insistió mucho en que diera la charla en inglés y lo voy a hacer así por toda la gente que está conectada en YouTube. Hello. A ver si es verdad que están ahí. Voy a ver si estoy a la altura de las expectativas después de esta introducción tan generosa. And what I'm going to talk about today is a recent adventure that we had with Daniel Peralta and Robert Cardona and Francisco Presas, who is not here. Where is Fran? Okay. So I'm going to start. It's a bit late. We all want to go and have lunch. Let me start. Do you remember this ad? This is the ad of Seat Toledo. If you don't remember, this is an ad from 2006. And let me project this ad. Let me see if it works.
On the 12th of January 1992, the merchant ship Old Susan, sailing the Hong Kong-San Diego line, was caught in a terrible storm and lost all its cargo. More than 20,000 rubber ducks. "14 years and 6,000 miles later, the inhabitants of Stratford in Scotland woke up to the unusual sight of thousands of ducks invading their coastline. Life is full of surprising endings.
Vale, es el anuncio de Seat Toledo. And the message of this advertisement is that, well, life is full of surprises, so you should buy the Seat Toledo. But the message I wanted to convey here is that what happened to these rubber ducks, indeed, this is an advertisement, so don't believe everything they explain. These lots of rubber ducks were supposed to show up in Scotland, but finally they didn't. And there is a nice story behind this ad, which is the trip of the friendly floaties. Before talking mathematics, let me explain a little bit the story, what is true behind this advertisement. There was a cargo which was carrying a lot of things inside the cargo. This was the Everlaudel, and Everlaudel departed from Hong Kong to go to Tacoma, and there was a storm. And in this storm, there were 29,000 rubber ducks, which were lost in the ocean, okay? And this was in January, and then in November, there were 10 rubber ducks appearing in Sitka, Alaska. And then, as you see here, I should use this because otherwise the people in YouTube don't see. There were expected a lot of them to arrive in Scotland. But the truth is that only one appeared in July 2007, and the advertisement is 2006 that you saw. One rubber duck showed up in Scotland, so many of them were expected. These rubber ducks have been used to understand the currents, okay? And there's even a book that you can buy in Amazon, and it's Moby Duck, which explains the story of these ducks. And indeed, oceanographers have been using the movement of these ducks and other flotsam to understand the ocean currents. And here you have a picture of Curtis Evans Meyer, okay, who is, this is when he was young. Already the parents introduced him to first in the ocean. And he used indeed the movement of flotsam, so all the things lost, like all these Nikes lost in the ocean, to understand the currents, okay? And even there was a prediction, and according to this prediction, there should be many of them arriving in Scotland, okay? So these friendly floaties indeed were used to predict, but they didn't arrive in Scotland. Only one of them arrived in Scotland. And indeed, if you decide to send a love message inside a bottle, which is something that nowadays nobody does, okay? Only in these bad films that you see on Saturday, you can see these kind of adventures, like, I'm going to put a love message inside a bottle and throw it to the sea. Why do you do that? Send a WhatsApp. Okay, but if you do that, you must know that only 2% of the messages are recovered. And how is this known? Because Curtis Evermeyer and Jim Graham sent a lot of these bottles and put a message inside these bottles saying that if you give them the bottle back, they would pay you $50. And this is why we know that if you get this note, of course, saying this is $50, then you try to get these $50 back. So only 2%. This is a sign about things that cannot be predicted related to fluids, okay? And what I'm going to talk about today is an adventure that started not thinking of these things. Indeed, we started to work on these objects because we were working on these B-manifolds some time ago at the beginning of Robert's thesis. I told Robert, you're going to do a thesis on integrable systems on B-symplectic manifolds. He said, cool, okay? And then, well, he did, this was part of his thesis, but then, I don't know, we were taken, maybe by this unpredictability of fluids, we were taken to another interesting part of mathematics, which is the interaction between computational complexity and fluid dynamics. And, well, what I can say is that we have examples of complexity and indecidability of fluid dynamics, and we have this recent example of La Palma, okay? So we have this volcano, and it's unpredictable to know what will happen with this volcano. This is an example that we are seeing, and well, we have all these storms, and this beautiful picture of Kanagawa Sea, and well, this is another sign of complexity of fluids. And this goes back then, maybe you don't recognize, but the person here is Roger Penrose, okay? And he asked a long time ago if we would be able, indeed, to imitate, I mean, if a computer could work as a mind, as a human. And he wrote a book, which is Pop Science book, but there is a question and the question behind is that, can a physical system be complicated enough to make computations? This is a question which is not pop science, but it's quite realistic that he was asking. On the left, on this picture, you have Moore, okay? Moore asked if fluids are complicated enough to create a computer. And then Tao revived this question. He asked this, Moore asked this question in 91, and Tao revived this later in 2017. So the question is, well, are we talking about complexity of fluids? We should also think about complexity of computation, and we should think about Turing machines. So the question is the complexity of fluids enough to simulate any Turing machine? So here we have an image of storms, complications, and Turing. And I should recall a result, an important result by Alan Turing, proved in 1936, which is the proof that the halting problem is undecidable. What is the halting problem? This is a problem that is a problem in computability theory, but it's also a problem in logic. At the beginning of last century, they were more or less hand in hand, attempts to understand, Gödel from logic point of view, and from computational point of view, Turing. And the question is there a way to create a kind of supercomputer that can detect if a computer will halt or not, will stop or not, okay? And that's the halting problem. And Alan Turing proved that you cannot find such a supercomputer, or if you want such a general algorithm to solve the halting problem for all arbitrary computers, or if you want, you can think of programs, of pairs of programs and inputs, okay? And this is also related to Gödel's theory of completion of Gödel and so on. But let me recall the proof. I'm going to do a proof by picture. I took these pictures from computer field, which they have a very nice, in YouTube you can find a very nice video explaining this construction. Imagine that you have such a machine, okay? Then you have this machine here. This is the super machine. Imagine that you have a machine that for a certain program, okay, this should be the super machine, that it tells you that for a certain program, okay, and a certain input, it halts, okay? Then, well, I'm going to assume that, let's think of a computer like a yes-no process, like a Windows computer, okay? So, okay, if such a computer exists, if we have a computer that can decide if something stops or not, the idea of Turing is, okay, let's tune a little bit this supercomputer, and let's create a new computer, which is called H+. And this computer, what you do is to add some extra bits to change the outcome. So if the answer is yes, then we change so that we automatically program the computer to change so that it makes loop. This sign means that it should loop forever. And if it doesn't halt, then we change so that it halts. So in a way, this is something we can do, because if we set a computer, we just manipulate, we just tune it a bit, and it becomes this supercomputer H+. But there is a problem, that we can always feed this supercomputer H+ with itself. And if we feed H+ with itself, we get a contradiction. Because if it has to stop, if it halts, then it doesn't halt. And if it doesn't halt, it halts. So where is the contradiction coming from? It comes from assuming that you can have such a machine, super machine, okay? And that's a very simple proof of the halting problem, okay? And we've seen also this, now that I see David is there, where is Fran? Fran is still not here. But we see that there is this undecidability in physics. David Perez proved some time ago, okay, also as a consequence of the halting, of the undecidability of the halting problem, that a result in physics, which is the following. I'm going to state it very thoroughly, forgive me. Indeed, I was watching one of your videos and I even took this snapshot. There is a very nice talk. I recommend everyone to see this talk in YouTube, a talk that you did it at ANS on indecisibility in physics. And the question is, given the Hamiltonian of a quantum many-body system, is it gapped or gapless? And the gap is the difference of energy between the ground state and the first excited state. And, well, David Perez proved, together with Kubit and Wolff, that the spectral gap problem is undecided. And this is another nice application of the fact that in their construction, okay, they relate this to Turing machines. Indeed, the purpose of my talk is to take this idea of the halting problem to the world of fluid dynamics, and to answer the question by Moore in 91. Okay, so this is a little bit the chronology of what I will explain. I always tend to be unable to finish my talks, but it's okay. I think I'll try to manage to convey some ideas. Of course, I will not be able to convey all the details of the proof, but for that, maybe there are other more technical talks where I can provide such details. So a little bit the chronology starts with Moore asking if hydrodynamics is capable of performing computations. Then we have this story of the ducks, right? 29,000 rubber ducks lost in the ocean. Then in July 2007, one rubber duck shows up in Scotland. And 10 years later, tau asks about universality of Euler flows. I said, okay, what tau has to do in this story? I'll get to that. And indeed, how we started working in this was that with Robert and Daniel, we had been working on extending a very nice mirror from contact topology to fluid dynamics for B manifolds, so for manifolds with boundary. And then it turned out that on my way back, I was in the train and I saw this question by Tao. It was in Twitter. Okay, what I was doing in Twitter. In Twitter, you find questions. Okay, it's interesting. And well, we had like this idea that maybe we could try to apply these tools from contact topology. And this is where we started to work on this. The question of tau, indeed, was a question about universality of Euler flows. So in a way, tau, what do we mean by this universality of Euler flows? We mean if any dynamics can be seen as an Euler flow. Is this question, I mean, if you think about this, you may have very simple dynamics. Why do you want to represent these simple dynamics as an Euler flow? Well, it's a matter of, arranging things. We can say that Euler flows, it's a box, okay? And this would tell you that this box includes all the possible boxes in dynamical systems. But of course, there is a price to pay for that, which is that this universality maybe cannot be attained in your initial manifold where you have the problem, and you need to increase the dimension of the manifold. And this is the result we prove. We prove that by increasing the dimension of the manifold, any dynamical system can be seen as an Euler flow. Indeed, as a particular type of Euler flows, which are called steady Euler flows or stationary solutions. Okay, so this is the result that we proved. This we proved in November 19. We posted on arXiv. In November 19, in October, I had been here, pre-pandemics. I had been here for 2 months or so, living in Madrid. We were working very hard on this business. And the kind of techniques we used are from contact topology. And then in November, I went to Zurich to give a talk in the analysis seminar. And I was very happy about this result. I said, oh, I'm very happy. And everybody could see, oh, you're very happy. So in the questions, they say, oh, you're very happy, but here you are proving that you have to go to dimension 17 to do this representation. I said, yeah. And what about dimension 3? Come on. I mean, we are interested in dimension 3. So, well, I remember talking to Daniel, people in analysis didn't like my talk. They said, okay, we have to prove something in dimension 3. So we started to play a little again with contact geometry, and this is the kind of games I will explain today. And then we prove that there exists another stationary, what we prove is, okay, this universality, you cannot avoid increasing the dimension, but indeed a consequence of the universality construction is it's a construction that is Turing complete. I have to explain what this means. And we could attain this Turing complete, not the universality, but the Turing completeness, using dimension 3. Okay. And then, of course, well, also people in analysis could complain, well, but you are working with stationary solutions, right? From a geometry, this is very nice. But if you look at this box of Euler flows, this is a very small box. But it's very interesting. We are proving that it's very complex. It's very complicated. But we could also prove later on with Robert and Daniel that we have, we could improve this construction to attain time-dependent Euler flows, which are Turing complete, at the price of increasing also the dimension. And the proof in dimension 3, which is the proof that inspired this metaphor of the rubber ducks, because, well, indeed, the message is that it's undecidable. I mean, our construction, we provide a 3-dimensional Turing complete, and therefore, because of this halting problem, the conclusion is that some fluid paths are undecidable. This would explain why you cannot recover these bottles or these ducks. But still there is a complaint, because our construction, because it uses strongly geometry, it changes the Riemannian metric. This means that we cannot assume that the Riemannian metric is the Euclidean one in this three-dimensional construction. But this is something we have been able to very recently address with very different weapons. And this is something I will have no time to talk about, which is a recent result in November that we posted on the archive at the beginning of the month with Robert and this is a little bit the chronology. Okay. Now, I have to say that what I explained is joint work with Robert, Daniel, and Fran. And the first paper, the one I like so much, is still a preprint. This happens, you know, pandemics. And then this construction in dimension 3 was published in PNAS. And then this construction T-dependent was very quickly published at the MRM. Okay, let me include, well, I mean, I have spent already a lot of time, but let me give a general, now I'm going to introduce, I explained a little bit the ideas, but I didn't give any definition. So I'm going to define everything I use, and I'm going to try to convey these ideas of combination of techniques. So which kind of equations are Euler flows? I look at incompressible fluids on Riemannian manifolds. Well, first I look at incompressible fluids on R3, okay? And these would be the equations defining incompressible fluids on R3. Okay, this second one is the divergence of x equals 0. By the same mnemonics, we can indeed, these equations, which are written, you know, using vector calculus and using the Euclidean metric without saying it, indeed, the mnemonics is the same if we now change the metric. Why we want to change the metric? We need to change the metric to solve our problem. But we just need to change the metric on a certain set. And I need to say that because these equations make sense also if we assume that we have a general Riemannian metric. And then instead of writing these equations like this, I can write it as a covariant derivative. Okay? So what are the unknowns here? The unknown is the pressure, okay, and the velocity field, okay, of the fluid. As you see here, I have an evolution equation that depends on time, okay, and here what evolves is pressure and velocity, okay, and well, first thing, as mathematicians, if we want to solve an equation or understand an equation, let's put ourselves in the simplest scenario. Maybe we won't be able to leave the simplest scenario, but it's interesting enough. Let's first assume that we don't have a dependence of this velocity in time. If we are taking this, if we have this independence, then what we have, okay, this first equation reads like this because I don't have dependence in time, and I have that the divergence is 0. Okay. Well, these equations are here using, you know, vector calculus. Okay. But well, I mean, in this group we were a bit geometers, right? So, we see a vector calculus equation and we don't get very excited. But if we see a 1 form or a 2 form, we start playing games. Okay. So this is what happens. What happens is that you can dualize these equations just in the following way. Okay. If you have this vector field x, okay, and you take a metric G, then you can attain a 1 form just by contracting the metric with the vector field. Okay. And then once you have that, you have this 1 form, and then naturally you ask questions about this 1 form. A natural question is if this form conveys some kind of geometry. Indeed, you can translate this first equation. Okay, this implies some computations, but this can be seen as the contraction of the vector field x with the differential of alpha equals minus the differential of a function which is called the Bernoulli function. Okay, that it's a function that you can express from the pressure, okay, and the metric. Okay, so this function, the Bernoulli function, is just the pressure plus 1/2 the norm of the metric. So here the metric plays a role. Okay, then let's talk about Beltrami fields. Beltrami fields are everywhere. Okay, well, what is a Beltrami field? A Beltrami field is a field that I'm going to assume that the divergence is 0, that satisfies that the curl of the vector field is proportional to the vector field. Why are these guys relevant? Because they are solutions to this stationary Euler flow equation. And if I give me examples of the dynamic fields, as geometers, the Hopf vibration is a good example. So Hopf fields are dynamic fields on S3. And from a point of view of dynamical systems, the ABC flows are very important in KAM, okay? To study chaotic behavior. And the ABC flows would be the solution to this differential equation. These are examples of Beltran, okay? Time to talk about Navier-Stokes. I mean, now I want to say why Tau was interested in this kind of problem. So what was the question of Tau and what was the question we answered? Maybe it's not the same question. Fran, hello. I have been asking, where is Fran? Where is Fran? Fran is here. For the people in YouTube, he's late, but he's here. So he's here just in time. Just in time. Okay, now that Fran is here, well, I mean, if you can solve any of these problems, you get $1 million, okay? This is not a lot of money by now. What can you do with $1 million in Spain? If you have 4 co-authors, maybe you can not even buy a flat, but these are important problems. So if you solve one of these problems, you become famous, I imagine. And in this list of problems, only one has been solved, which is the Poincaré conjecture. And the person never went there to take the money. So all the other problems are pending, okay? And one of them is the Navier-Stokes. One of them is the Navier-Stokes equation. Okay. What is the Navier-Stokes equation? So, well, it's a little bit more complicated than Euler equation, I could say. Here we have, like, if we look at the Euler equation, here we have, this would be the Euler equation case without these terms here. Okay, and here we have a term that implies the Laplacian. Maybe you don't see the ones more here, and implies the viscosity and external force. These are Navier-Stokes equation, and what I have done here, not very successfully because it's not very visible, but you can look at it online, is a description of Pfefferman of the Navier-Stokes equation problem in the clay list. So if you go to the clay list, there is a picture of Navier. And then they say, well, fluids, blah, blah, official description. Then Pfefferman explained what would be considered a solution to this problem. Okay, so this is like saying you have here Navier-Stokes equation and you have some initial conditions. Okay, and well, here he's just explaining that here, this is the Laplacian. And this is that if you take the viscosity equal to 0, then you get the Euler case. Okay, and then, well, here there are some conditions imposed because we want to find, okay, they want to prove existence of global smooth solutions. And Pfefferman explains what do we mean by global smooth solutions. First, solution has to make some sense physically. And this physically is all these conditions here. In particular, there is a condition on energy. And indeed, there are like 3 scenarios that Pfefferman is describing. The first one, solving it on R3. Second one, solving it on the 3 torus. And the third one, to avoid problems at infinity, assume that you have some kind of periodicity, and then the conditions slightly change. But here I just present the case of R3. Okay, and then the questions in the case of R3, otherwise if you look at the paper R4, are the existence of the smoothness of solutions, okay, or the breakdown of Navier-Stokes solutions are. So it's Pfefferman says, we consider the problem solved if you can do anything. So, well, I mean, these are hard equations. People have been hardly working on this. We are nobody to say anything about this, at least myself. But Tau, maybe we can think that maybe we could ask Tau, what do you think about Navier-Stokes? And Tau had an idea that he has been working on since 2007. In 2007 already on his blog, he posted a question on Navier-Stokes and said, why it's so hard to prove regularity? And then he was observing that Navier-Stokes, if you don't assume external force, have a kind of behavior up to rescale. And this later on was an inspiration for him, because he posted a note in Nature giving an idea, of course, nothing proved, but an idea. And this idea, I decided, like a metaphor, okay, the metaphor for the idea of tau, this idea of rescaling, would be to use Navier-Stokes. One of my PhD students is Russian, so from Russian inspiration, you take a doll, you open it, you have a smaller doll. So you have a rescaled version of the bigger doll, but a small. And the idea that Navier-Stokes admit some kind of rescaling motivated tau to formulate the possibility to produce examples of blow-up. And his idea, so his motivation was to find some kind of initial conditions or some kind of initial datum such that you can program it, plug it on the Navier-Stokes, look at the evolution, and then because the initial data are computationally very complex, then you have blow-up long term. So this is just an idea. There's no proof, but he asserted very clearly what he meant by program. He meant I want some condition equivalent to Turing completeness. Okay, because I want this to revolve to a scale version of itself, and maybe this can be used for Navier-Stokes. And also, parallel to this, he was interested in universality, in a way to understand universality of Euler flows, because his idea is, okay, the simplest version of Navier-Stokes is Euler flows. Is Euler flows good enough to find this Turing initial datum, which is Turing complete? This is the order of ideas. So the question of universality is also linked to this question. And this is what called our attention. Indeed, initially, this was the question of universality. When we started to read the papers of Tau on universality, we understood that behind this universality, there was also all this thing of Turing complete. So universality comes with this idea of having a box, the universal box, which is going to be Euler flows, inside which you can put any box, any dynamical system. In other words, let's go, if you go to December in Barcelona, doesn't matter which day, that's the kind of weather you find, sunny, nice way, okay? That's the typical day in Barcelona. If you go to Paris, that's the typical day in Paris. Well, except for this Santa Claus. It's not very French, but he was there in the picture. But, well, you can spot 7 different. So the message of universality is, okay, maybe your 2 dynamical systems are different, like Barcelona and Paris, but if you are far away, like in the international national, the ENSS, okay, maybe you cannot see the difference. That's a little bit the metaphor here. The metaphor of if you look the system, the dynamical system from far away, maybe you don't see the difference. Well, still you see the difference because the number of lights, but well, I'm not going to discuss this. Time to introduce new tools, okay? When we were looking at this question, as I said, we were looking at this question by Tau in the right moment. I mean, sometimes you start working on a problem, nobody cares. Well, this is the standard thing, okay? But then out of the sudden, you are working on your problem, nobody cares about this problem, but out of the sudden, somebody is asking a question in the right moment and the right place. This is an example of the right moment and the right place. We had been thinking about some techniques in topology to work in fluid dynamics, and the question of Tau that we saw on Twitter came in the right moment. So it's time to introduce a little bit contact geometry and to say what is the relation of contact forms with Peltramic fields. Okay? Do we need symplectic geometry? No, but I like the camel, so I left the camel there. Also, well, I come from symplectic geometry. Okay, we could say that symplectic geometry. Okay, here I use some controversial colors. I realize I use red and blue because Barcelona. Okay, I didn't mean that, but well, what symplectic geometry would correspond to the even dimensional case, and contact geometry a little bit to the odd dimensional case. Today we can forget about the even dimensional case, but I'm going to leave the camel there, which is a nice representation of what people in symplectic topology are working on, which is the non-squeezing theorem, and I just need to talk about contact geometry. And what they have in common, symplectic and contact geometry, is that it's the geometry of forms. In the case of contact geometry, we need a one form, okay? We need a not dimensional manifold, and then this one form has the condition that alpha wedge the alpha end different from 0. In other words, that alpha wedge the alpha end is a volume form. And well, there are some interesting things going on, which makes contact and symplectic geometry so different from Riemannian geometry to the ones that are maybe more standard to study on an undergraduate course. And well, the first thing is that locally there are no invariants. And this is because of the Darboux theorem, also in the contact case. Locally, all contact manifolds look the same. You say, oh, how boring. Huh? No, there are interesting things. For instance, from a point of view of dynamics, an interesting vector field would be the Rep vector fields, okay? Which American people pronounce as RIP, but I insist on pronouncing as Rep from just Rep, and which are given by these two equations. You have this one form, okay? And then you assume that the differential of alpha, the differential of alpha is going to have a kernel, and this Rep vector field is going to be in the kernel. And then you have one direction of vector fields that is going to be in the kernel. You just need to take one, and you take the one that satisfies that alpha are equal. Okay? And then, well, of course, you have some kind of Hamiltonian dynamics. But I will not talk about Hamiltonian dynamics today, so I'm going to skip. Now, I just wanted you to know the definition of contact structure. But why do we care about contact structure? Well, here an example. This would be the case of R3. And well, here a computation, and a down-to-earth computation. You take the standard contact structure, you look at the kernel, and then Frobenius theorem, this is non-integrable, okay? And this is equivalent to the condition that alpha wedge the alpha is different from 0. This is equivalent to the condition of non-integrability of the distribution given by the kernel of the one form alpha. So this could be a problem here on an exam on the last year, okay? So, well, this is an example. And the condition of non-integrability here, what we have pictured here, is precisely the kernel of alpha. And the fact that the kernel of alpha is turning, is an inspiration to say that this is non-integrable. But, okay, let's talk about down-to-earth things. Why is contact geometry cool? Well, it tells you that you can park a car. Well, we know that you cannot park. We know that there is no such a thing as parallel parking, right? You arrive here. Well, we arrive here. It's impossible to park. But okay, in general, it takes several attempts. At least you need 4 attempts, according to the theory. Indeed, you can use contact geometry to prove that you can always park a car. This is very cool. This is a theorem. This is a theorem indeed of a paper by Emmy Murphy, when you can prove that a car of length L can be parallel parked in any space of L, you need an epsilon. And this epsilon depends on how you are parking and who is the owner of the other car, okay? So, well, here you have a contact, you can have a contact structure, you can prove this kind of things. This is very cool. But other examples, the Hopf fibration, okay? I have here 2 representations of the Hopf fibration. The first one using complex geometry, and the second one is the clever one, the one that you already write things in Hopf coordinates, but it's a representation of the same thing. Indeed, this is the meme. Wait, it's all Hopf fibration. Always has. Okay? Well, you have this meme with linear algebra, with Hopf fibration, with whatever you want. Okay? And indeed, so this tells us that Hopf fibrations are an example of Rep vector fields. Here you have the one form, blah, blah, and you do the exercise. But it's also an example of Beltrami field. We said this, okay? And it's also an example of Beltrami. So it's an example where the same vector field is Rep and Beltrami. How cool is that? Well, there is a mirror, and this is a theorem indeed. This is a theorem that if we look at the stationary Euler equations, which are this one, already written with the eyes of a geometer, with one forms, then the one form given by the contraction of the metric with the velocity vector field is indeed a contact structure, okay? And then if you have a red vector field, okay, and so there is a one-to-one correspondence between Beltrami vector fields, we need them to be singular, not to be singular, sorry. This condition of rotation are non-singular, that they never vanish, okay? That the function that multiplies them, the condition that we have of Beltrami field, is that the rotation are always proportional to the vector field, and this proportionality factor is always positive, okay? And also we assume that this vector field doesn't vanish. Then you have a one-to-one correspondence between red vector fields and Beltrami vector. And this is what we were working on, and extending this mirror to be manifold, which we did. We also extended it to higher dimension. And now the cool thing is that you have a mirror. And this is Ednar and Grice, the ones who proved this. Ednar looked himself in the mirror and became Grice, no? I mean, well, you put a problem in fluid dynamics, and you want to solve a problem in fluid dynamics. You say, oh, I don't know fluid dynamics, but I know contact geometry, okay? So I look myself in the mirror. On the other side of the mirror, I become Fran Presas, okay? He's an expert in contact geometry, and he solves the problem in contact geometry, and then we just need to translate this solution in fluid dynamics. And that's the trick. Indeed, this idea is very good for extending known results. For instance, you can apply Weinstein conjecture for red vector fields, which tells you that any red vector field, I mean, this is a conjecture by Alan Weinstein, that any red vector field has to have at least one periodic orbit if the manifold is compact. This is proved in dimension 3. At the moment when Ednar and Grice wrote their proof, this was not proved. The proof came later. But it was known for S3, and in their paper, you can see applications to prove existence of periodic orbits for Beltrami fields. And well, one thing you can do, and this is the game we played, is, I mean, you want to prove something about universality of Euler flows. You look yourself in the mirror, and this, I mean, if it's a Beltrami field, you get a red vector field. And then the question is no longer a question about universality of fluid dynamics. It's a question about universality in contact geometry, and it's a question about universality of red vector fields. Okay? And this took us to the H principle, which is the way to deform things in contact topology. And this same idea worked very well. This gave us the construction of universality, and this same idea worked very well to give this construction in 3D of universal Turing machine. These are the ideas. And let's see, what is the geometrical approach to the question of tau? The question of tau is, can any incompressible vector field be embedded as an Euler flow in higher dimensions? If we look ourselves in the mirror, if we are considering the Beltrami case, yes, it's putting ourselves in a smaller box. But it's very cool because we said that this smaller box is good enough to put any dynamics. And well, this question automatically, you look yourself in the mirror and it's a red vector field. And this question becomes, can we realize a vector field on a manifold as a red vector field on a bigger compartment? I remember the first day we thought about this. We were in the office with Daniel, and Fran was not there, so we sent him a WhatsApp. Is this true? I thought everyone in contact geometry must know this. And he said, eso es más falso que un Judas de plástico. This is faker than a... And then 5 hours later, he told me, this is very interesting. And now I don't know what I did. Where I am. Okay, here we are. He told me, this is very interesting. Well, the first day we were trying to prove this, we didn't realize that we need a condition on the vector field. And when you think about this, this is very natural. We need a condition that the vector field is geodesical on the manifold. And well, the first question is this condition sufficient? And the second question is, how hard is to get such a condition? Let's recall, what is a geodesical vector field? It's a vector field for which there is a Riemannian metric such that the orbits of this vector field are geodesics of length 1, okay? And there is a very nice characterization by Hermann Gluck, which tells you that this is equivalent to having a 1 form, alpha, such that alpha of x equal 1, and the contraction of x, because the differential of alpha is 0. And now you say, wait a minute, these are the conditions of alpha. These are the conditions of the red vector field. Aren't they? Yes, but this alpha is not necessarily a contact form, okay? And then what we thought is, okay, if alpha is not a contact form, let's try to make it contact by deformations. That's the idea. And this took us to the H principle. So the second question, of course, at the beginning, we said very silly things. This is the way you work until we found this condition. How hard is to get this condition of geodesical vector field? Well, if you allow yourself the possibility to increase the dimension of the manifold, it's always possible to do such a thing. If you start with a periodic vector field, if it's not periodic, then I'm going to consider now the periodic case to embed it on a compact manifold, okay? And it's very simple to say that the suspension of a periodic vector field is geodesical. It's as simple as this. You take the vector field, you do the suspension on the product with your manifold, initial manifold with S1, so you increase one dimension, your manifold, and automatically the condition of geodesibility of Hermann Gluck is that alpha, that you need to find a one form, okay, alpha, satisfying these two conditions. Automatic, it's one line. This could be an exercise in an exam. It's very simple. Variation in tactics. We needed to deform this contact structure. And who are the masters of the formation of contact structures? Probably, well, Fran is one of them, but Eliasberg, okay? Indeed, our inspiration came from a paper by Eliasberg, by Borman, Eliasberg, and Murphy, where they prove, by using the formation, that they solve a very interesting question, which is a natural question. If I have an odd dimensional manifold, is this manifold going to be a contact manifold? In dimension 3, the answer is yes. And in higher dimensions, the answer is, okay, if it has the right topology, it's going to be contact. And the right topology is hidden in this condition of almost contact. I'm not going to explain the details, but it's a topological condition. So in a way, they prove that topology implies geometry. That's what they prove. And what is the philosophy of the H principle? As everything in life, except for parking, which takes 4 steps, everything takes 3 steps. The first one is that you have a goal. And the goal is, I want to solve this equation. And then reality comes, right? You want to solve this fancy equation, but you can only solve the linearized or the formal equation. And you need a miracle. And the miracle is that if you solve the easier version of the equation, this is enough to say something about the complicated equation that you had at the beginning. And the miracle here is to prove that there exists a homotopy or a deformation that allows to deform a formal solution to a honest solution of your problem. And for this, people who work in H principle know that it's enough to have enough high codimension. And this is in a little way for us related to this idea of increasing the dimension of the map. So we could prove, and that's the first theorem that we proved using this mirror between contact geometry and fluid dynamics. And I should finish soon. So I'm very far from the end. I knew this would happen. But, well, the first result is that Euler flows are universal. So we could represent any dynamics, okay, as an Euler flow. And the combination, how to prove this, first, there is this trick of increasing one dimension to make it geodesical. And then, well, there is a way to put it on a sphere of dimension 4n, and then you use the H principle to get this dimension smaller. But the smaller is not very good. The smaller is 3 times the dimension of n plus 5, or plus 6, depending, because we need this to be odd, okay? And the idea of the construction, as we say, is to use this mirror. Let's go back to Turing. Time to go back to Turing. What is Turing completeness? Well, Turing completeness related, so we have machines, okay, and we have vector fields, and we need to relate these dynamical systems with machines. How do we do this? Well, if we have vector fields, we have the flow of a vector field, okay? And indeed, we have a way to relate this flow to the encoding of the machine in such a way that following this flow is equivalent to making computations with the Turing machine. And we say that it's Turing complete if the halting of any Turing machine with a given input, is equivalent to a trajectory of this flow, of this vector field, entering a given open. This definition, we found it in a paper of Tao, but it looks like, well, there are variations about this definition, but it's not time to talk about this. But what is important is that as a consequence of this universality, we could provide a construction of Euler flow, which is Turing complete. And the way to go is the following. First, Tao provided a construction on a 4 torus. So essentially, we just need to use our theorem first by increasing one dimension to get the geodesibility condition, and increasing this takes us to dimension 17. You make the computation. So we just as a consequence, as a corollary of our construction, we get a Turing complete Euler flow, Eulerizable flow. Eulerizable means that you can make it Euler in a higher dimension in a sphere of dimension 17. Okay, and I mean, how do you prove this? Was essentially what we are doing is promoting a construction of Tau, and the way that this construction is affected by the H principle, because the H principle, a way to look at it is algorithmic, okay? Then everything is algorithmic, and if the initial data was Turing complete, the final data is Turing complete. So this is a concept. But always the question, can we do it better? As I said, I was very happy about this result. I went to Zurich. Indeed, my last trip was here in Madrid pre-pandemics. No, my last trip was to Granada, but my last talk in a seminar was in Zurich, okay? And then I went there super happy, and then I was, well, they told me, well, what about dimension 3? So can we find an Eulerizable flow in dimension 3? And the answer is yes. We could find an Eulerizable flow in dimension 3, which is Turing complete, okay? But the metric is not the Euclidean one. It's the Euclidean one outside a toroidal set, where inside which we make the computation. So as a consequence of the halting problem, there exists undecidable fluid paths. So this gives an explanation why you couldn't find these DAGs of the advertisement. So going back to Navier-Stokes, does this give you finite time blow up of the Navier-Stokes equation? The answer is no, because if yes, then I would have, and Daniel, we would be sharing all this money, and we would be making a party, right? So we didn't get blow up. Indeed, if you want to look at the details, now it's very technical. I put here the details, but look at the paper, okay? So this is not good enough to find this blow up, okay? This initial construction. Here is a picture of a Turing machine, because what I have been talking about Turing machines, and I want you to think of a Turing machine in my last 5 minutes as a printer of some states and an alphabet. And here I have this kind of infinite stripe where you look at this as a printer. And you have a kind of user's guide of this machine. And the user's guide is that if you start off there is like the initial state, which is the Q0. There are two very important states, and the halting state, which is the state in which the machine is going to stop. Okay, so if your current state is the halting state, then this holds the algorithm, and the output is precisely T. Otherwise, how does it work? Then you just keep on advancing the line, and you advance like with pair of states, where you have -0 or 1, which tells you if you go to the left, to the right, or you stay in the same place of this infinite stripe here. Example. So here you have a Turing machine. Here you have this, you think of it as a printer. And then if I go from Q0 to the next step, and I have a +1, then this infinite stripe moves to the left, okay? And if you don't like to think of this infinite stripe, you can think of Conway's way of life. This is a system with 0 players, so, well, it's a game which is not very funny, right? Because you don't have any player. So you just leave your machine, and I mean, there are some, I mean, I will not give the details of the Conway's game of life, but it's about survival and death of things, and you have some rules telling if they will survive or die, and you can leave this, go to teach your classes, you come back, and this is university working. So it's a game, and indeed you can think of a Turing machine as as this kind of games, because this is a cellular automaton, and John von Neumann proves that it's equivalent. So you can take your favorite one. So this is the definition that I said of Turing completeness. But just to finish, how did we provide this three-dimensional proof? There is a hidden dynamical system inside any Turing machine, and this is a bit technical, but it's the notion of generalized shift. So shift is moving things, and generalized shift is like moving two things. And Chris Moore, already himself, he gave a construction of this. I mean, he proved that if you have a Turing complete system, then you have this generalized shift, and that you can relate this generalized shift as mappings of the Cantor set of the Cantor square, indeed. So, indeed, Moore, well, this wants to be a square, okay? And here inside this square, you have the Cantor set, where you use already a predefinition, which Chris Moore did. And what we did is to extend this to find an area preserving the diffeomorphism of the disk. And you say, okay, you say this, but this disk is two-dimensional. And you are telling me that you use this construction to make it Turing complete. How do you do this? And why do you get a Beltrami field after all? And the answer is, look at the mirror. What we do is to repeat this trick of the geodesical vector field, okay? We just need to suspend this two-dimensional Turing machine, extension of Turing machine, that we need to be volume preserving, blah, blah, okay? Because what we prove is that if we have an area preserving the diffeomorphism of the disk, then we can always extend so that this is like the Poincare section of a red vector field. And if I have a red vector field, I have a contact structure. So I look myself in the mirror and I get a Beltrami field. And why is this Turing complete? Because it comes as an extension of a two-dimensional Turing complete by a suspension, which is totally algorithmic. So this is how our three-dimensional proof works. And I think that with this, I'm going to finish. I think I started like 55, I mean, I started a bit later because there were all these presentations, but I think this is a good way to stop. And we proved more things, but I will not explain it, too many information. So what's next? One of the things that I'm here for, I'm here to give this colloquium, but this week we should understand the relation of this computational complexity with topological complexity, together with Renzo Bruguera, who is there, okay? And Robert Cardona and Daniel Peralta Sala. So this is one of the reasons, besides accepting this nice invitation to be in Madrid. Of course, there are many other reasons to be in Madrid. It's a wonderful city. But with this, I think it's a good place to stop. So if there are any questions.
Thank you for this fantastic sentence and inspiring. So, do you have any questions? I think you have any questions, please, or comments? Questions or comments in the audience?
Brad, do you have any questions?
So you said that for the Euclidean geometry you need extra tools. Can you say something about
Yes.
those tools?
Yes, indeed. I mean, I can say that this construction works because this mirror, let's say the dependence, the way when you change the contact structure, it's like you change with this H principle, you deform the contact structure, is equivalent of deforming the metric. So you cannot prescribe the metric and make it. So the new construction is totally different. We couldn't use this. We do another construction, and of course it's not compact. Okay? So the construction is on an Euclidean R3, but what we did is like, because it's not compact, because we couldn't really make it compact, we get some approximations, some finite tape approximations, which are a good substitute or replacement of compact. If you look at the paper, on the archive, this is not very, I mean, it's quite technical, it looks very technical. Maybe we should find a survey of that because it's quite technical, but the idea behind was to try to make it as compact as possible, but we couldn't make it compact, but at least we have some, let's say, compact approximations of something that it's a finite thing that has a good computational power. So this is so the kind of tools are very different. So no contact geometry at all, no contact geometry. It's very exciting. I mean, of course, I mean we went out of the contact geometry. Also, we go out of the contact geometry work because one of the critics you could say is, okay, you are just playing with a very small box, the small of Euler of the drumming fields, but about Euler, what about time dependent? So then if you do this time dependent, then you don't have again this mirror, because this mirror only works, let's say, to say, like in a way, on the first slide of my presentation, there is like this is a little bit now our idea of geometry, and our idea of fluid mechanics could be this thing like complex. And our idea of geometry is that it's very simple, right? Indeed, this is a picture by Patrick Masson of this Hopf vibration. But at the end, what we are seeing is that already the simplest case is very complicated, but the tools don't work at all on the t-dependent case, because the t-dependent case we could say it's not geometry. And well, there have been attempts to understand if there is a geometrical path, because the geometry is very powerful here, but it seems that it's not geometrical. So it's like we are lost in the wild.
Thank you. Other questions or comments? Please. So one question. Now that you have this fluid that is still complete, and in principle the question was whether we can use fluids to make computations.
Yeah.
Now, what about the practical part? So how then you make these computations?
Yeah, exactly. So the idea is that can you make really this water machine? And Paris was talking about. My father is like, really, you did a water machine? How wonderful! I thought that you were a mathematician, so you did something with your hand. No, so of course, first it's not constructive. It's not physical. It's constructive. It's not physical because the metric is not sound. So we could say it doesn't correspond to a physical metric. The one we made, the one we just posted on the archive in November, that's physical, but we don't construct. I agree with you that it has potential, and we didn't exploit the potential of this construction. But I'm not ready to say anything else about this, because like it would be cool really now to take somebody who can really program this machine and try to see how far you can get with that. We still didn't do this. I mean, it's very recent. Like the proof that we provide is 100% physical. So it's really a water machine. So we could really say, well, these are water machines. So I could tell my dad, yes, I did a water machine. So good.
But imagine that this could be done. Then how will be the process to use this machine to copy? In the sense that, I mean, a Turing machine is something which is discrete, in some sense, while this flow is something which is...
No, well, yeah, but precisely, well, I mean, yeah. So the difference, let's say, between the dynamical system and the machine is that there is no encoding. And the question you are asking, indeed, is if you change the encoding, can this change? And the answer is it looks like it change. So it depends very much on the encoding. I'm not going very deep in the proofs because it's not the place to do this, but it depends very much on the encoding. But you can really encode things. So you could really program things, and then the applications, we still don't know. We still don't know. But it could be possible to make a computation. This would be interesting. I mean, we started to think of this because of the question of time. So looking at that, the question is not the question of time. I mean, do you have the finite time blow up? I mean, in that sense, this construction doesn't meet the blow up. Also, we don't know if, like, because, okay, the approximation of tau to the problem, how can I say this? It's not very precise, okay? Because still details are not understood. Okay? So maybe there is a way to plug these solutions in a different manner to generate blow up. This we still don't know. Also, we are, I mean, I don't know. It's an interesting question. I'm saying that still we don't know how to do that.
Thank you. Other questions or comments? Please.
What about non-deterministic Turing machines? Is there an analog of this theory for non-deterministic? I mean, I know that non-deterministic Turing machines is something about complexity. It's not about the ability of computing, but maybe there is some kind of analog in which you have some external force and you can put the external force in the fluid or not, and that bifurcates the flow or something like that.
Yeah, indeed, it's very interesting what you just said, because we are thinking of things that relating to this external force. I mean, the computational complexity we still don't understand. So, well, one important problem that we have is that the literature, like the literature in computer science, you need to spend a lot of time in translating. Well, you know this very well. You are one of them. So we are trying to do these translations, but there is no one-to-one correspondence. So I wouldn't make any experiment, but I can say that we are now playing with this external force a little bit to say where we go. I don't know. It's an adventure. We don't know where we go. We started to think about this occasionally, and now we are looking at kind of problems that, okay, as I said, Robert Cardona was supposed to do a thesis on integrable systems of V-symplectic manifolds. He did something about integrable systems of V-symplectic manifolds, but if you look at the thesis, essentially, we started to think about these things when he was there, and like, he has been an essential key person in the collaboration. He is the one who understands better this translation of computer science. We still don't understand. So there are many questions in complexity on computer science that we are, tempted to say this means that it's our complexity, but I don't know. I think we need first to understand the dictionary before making any final assertions. It's a good question.
Okay, so if I may, I would also to ask a question. So, in the relationship between complexity versus chaos. Because actually I was really puzzled reading the last paper of yours concerning the existence of these trajectories with zero. So it seems that they are undecidable, but not so chaotic in a sense, right?
Yes.
So if you can comment something about this, in particular, let's know if these are rare trajectories in a sense. I think they are non-typical, right?
Yeah, well, this construction that has zero entropy is that in our last paper, it's a restriction of something that it's in dimension 2. So finally, it's not the Mittani field, but it comes from it's an outcome of the. So it tells you that there is a slide somehow of your dynamics that is very simple. This is indeed the kind of things that we have to understand with Renzo and Marianne. How far can you say that? I mean, you have, let's say, the conclusion a little bit is that you can have zero entropy with complexity. And then maybe you need to refine your definition of topological entropy and look at polynomial topological.
This is what I was thinking about.
Yeah.
Redefinition of the topological.
But then you come out to the problem that, again, because your problem is using an encoding, and if you want to relate it to the Turing machine, we don't know which of, now we are in the problem of understanding which of these complexity, which is intrinsic.
Yeah.
Does it depend on encoding or it's not? So it's the kind of questions we are writing. We still don't know. We are working on it. So yeah, but it's a natural question. Like, well, indeed, like there in that paper, we got a construction that you restrict to dimension 2, and then dimension 2, everything has. Which I didn't know. I should know this because some years ago I was thinking about this problem. But then for the original system, we still don't know. We are working on this. It's undecidable, Indeed, I had problems. I said I had problems with me, my little rubber duck that I take for my dog. But yesterday when I got here to Madrid, I opened my bag and said, "Where are the rubber ducks?" I forgot them at home, or maybe it's on the side on that day. But usually take my.
Thank you. Other questions or comments? So, okay, if not, let's thank again the speakers. So thank you.
En YouTube había preguntas. YouTubers, no questions.
No question from you.
All these 100 people on YouTube, that's why I'm speaking English.